Hi, my name is Daniel, and
My name is Ethan, and today we're going to be presenting basically the design process behind our robot for RCJ Rescue Maze. So to start off with, I'm going to show you a render of the robot. So it looks something like this. So our goal for this robot was to get basically the smallest possible robot that we could for this, because in Maze, a small size it turns out to be a really big advantage when you're navigating through this maze. So very early in the design process, we realized that if we wanted to get anything this small, which is, I think, only it's a little bit more than 10 centimeters across. I think it's like 12 or something. If we wanted something to make a robot this small, we would need to create a custom circuit board. So then that's where we started by laying out a schematic of everything. So actually, while this looks complicated, most of it is just copying and pasting from existing designs, because a lot of the time you don't need to come up with something original. People have made these circuits before, and oftentimes also have the circuits released. So, for instance, we have a motor driver in a corner, and then all of this circuitry and the transistors and whatnot, that was just straight up copied from a breakout board by, I believe, Plolu. Because if it works, why bother changing it, right? So after we have everything thrown onto the schematic, we can lay it out into a circuit board. Wow, the contrast on this projector is terrible, but basically this circuit board is the base plate of our robot, and also all of our sensors plug into here. So by making it with the circuit board, we eliminate all the wires that you would normally need to connect between, say, an Arduino and all of your sensors. And instead, we just have a single wire per sensor that plugs into a socket on this board. So all of this was designed using the open source software KiCad that you can see up in the corner there. And then so after that, we have more or less assembled board. But that's only half the robot, because we still need the rest of the hardware on it. So that's where all of our 3D printing design comes in. So we primarily used FreeCAD for this, because, again, it's free and open source. And we designed all of these pieces as different interlocking parts. So if we go back to this visualization, we can take this apart really quickly and see what we have here is all of the 3D printed components are generally small pieces that then slot into each other to form the entire assembled robot. So this way, if we want to change, whoops, that is the wrong button. But this way, if we want to change any of these parts, it's relatively simple, because we just need to print. Say we wanted to change one of the sensor mounts, we just reprint the sensor mount, pull out the old one, put the new one in, and then that's that. So that saves us a lot of time on iterating on the design, because otherwise parts would take forever to print. Like, for instance, the dropper mechanism in the back of the robot, that's the only single large piece in the robot, and that takes over 12 hours to print. So if anything else was that large, or particularly that tall on the printer we were using, it would also take a really long time, and it would be really difficult to actually get any changes made because of that. So we're just going to continue looking at the design here. So you'll notice at the bottom here, we have these Omni wheels. So these are the types of wheels that you'd normally see on a soccer bot. And I know you can't see very well, but basically what's going on here is that the wheel has small rollers on it perpendicular to the direction that the wheel is rotating. So say if the wheel would rotate this way, they have small rollers that go in the sideways direction. So this is commonly used on soccer robots so that the robot can go in all directions. So you'd have two facing this way and two facing this way, which is called a holonomic drive. But we didn't want that because that would take up too much space, because you need one motor facing in each direction. By doing this, what we essentially did was we took our old track platform that we originally had, and then we bolted these wheels on top of it, because we were having issues before with the tracks falling off and just generally not having enough traction. So then we just put 3D printed these wheels to put on top. And because they had the rollers on it, the robot could turn in place easily without it jumping up and down, because when it turns like in place, the wheels have to slide sideways. So then the rollers on it allow the robot to do that. And also because it's bolted onto the track system, the old track system, we have basically 4-wheel drive, because the front and the back wheels are linked together by the tracks with only 2 motors, which means we don't need additional motor driver hardware and also modifications to the chassis and all of that. So that allowed us to get the maneuverability that we needed out of the robot. And then now we're going to go continue on to the front of the robot. So you'll notice there's a mirror on the front of it. It does not look very good in this render, but trust me, that is a mirror. And the point of that mirror system is so that we can have a single camera on this look at both walls on the left and the right side of the robot. So one of the parts of the maze challenge is that you have to recognize these so-called visual victims, which are letters on the walls. And to do this, we only have space for basically one computer on here. So because we didn't want to deal with having multiple cameras attached to the one computer and figuring out which one is which, we stuck with the one camera. And to make that work and still have it be able to look at both sides of the robot, we put this mirror on top so that the camera is sitting there looking up at the mirror and it can see both sides. So if we go take a look at this, you can see we have basically a sandwich around this board in the middle, that blue thing, which is a NanoPi Neo Air. It's a tiny, like 40 by 40-ish Raspberry Pi equivalent, which gives us the compute power that we need to be able to run all this vision processing stuff. And we'll be going more into the vision stuff later. And you can see on top, we stacked the camera so that this entire thing is a self-contained module. As you saw in this animation, this entire thing is one unit. So we can actually just pull that out of the robot as one piece, disconnect a couple of wires, work on it, and then put it back in, just like that. So by putting the camera and the computer on one unit, everything that the computer communicates with for the vision system is in one piece. And then the only thing that's left is a power line and a communication line to the rest of the robot. And now if we go to the back of the robot, we can see this dropper mechanism that I talked about earlier. So this mechanism is designed so that we can drop kits on both the left and right side, like that. And because the mechanism has a spring-loaded component, so if we open this up, you'll notice at the bottom there's a wedge that pushes up these blue rescue kits that you saw falling out of it earlier, up into the top of the mechanism. Because we have that going on, we can put all the kits underneath the point at which it drops. So you'll notice here that they come out of the top of the robot, right? And we need it to be that high up, or else it won't actually make it to the ground and clear the rest of the stuff on the robot. So that way, because we have this spring-loaded mechanism and our kits are below, we don't need a giant tube going up into the sky to fit all of our 12 rescue kits in. We can put it below and save a lot of vertical space on the robot. So then again, that is all assembled together, and then there's a servo motor to drive that thing that's spinning over there. And we also, in designing this, we also used a lot of our CAD tools to simulate the physics. So what I did was I exported the model of the dropper mechanism into Blender, which is normally a 3D animation software, but also has a physics engine in it, which allowed us to actually test how well these kits would drop out and slide without having to do the 12-hour print job for the dropper mechanism, because the thing is so tall. So that way we were able to make sure the kits would actually fall out without needing to go through the time-consuming process of making a physical model. And as you can see, I can also import the models into this game engine here and run these live demos with the physics and the fallen kits. And I think that's all we have to talk about the the hardware of it. So I'm going to turn it over to Daniel to talk a little bit more about the vision software on it.
So Ethan talked a lot about how we focus on making the robot itself really simplistic, efficient, and compact and modular as possible. And so this design philosophy really continued into our software development as well. And one portion of it that we're going to showcase is our vision module, which really exemplifies these qualities. So the task we were given was, as he mentioned a bit, it was part of the RobocupJunior Rescue Maze competition, in which the goal was to not only detect but also distinguish between the letters H, S, and U. And the goal was for a robot to traverse a maze while actually simultaneously detecting and recognizing these letters. And the goal is to simulate sort of a rescue environment. Maybe a robot is given a vision system, is trying to use the vision system to not only find victims, but also distinguish their status and what kind of aid they need. But before we can go into the software, Ethan's going to go a bit into how the hardware relates to this task in particular.
So again, as I said earlier, we have major size constraints that we kind of imposed on ourselves in making such a small robot. So that combined with what I said earlier about how we can only really fit one camera on one board without having a whole lot of other issues to deal with means we only had the space for the one camera, and then we had to use this mirror system that we talked about earlier. So here you can see, this is a render of the camera's perspective of this mirror. So you can see it sees letters on both sides, and this allows us, with basically just simply splitting the image down the middle of the frame, to get a left side and a right side with only one camera.
So for software design, we chose to use Python with the OpenCV library, which is a pretty common image processing library that has a lot of the features that we need in order to properly process the image and distinguish what letter it was. So we split up the task into really three portions. The first part is pre-processing. The goal of pre-processing is to turn this image we get from the camera and make it into something that's both easier to use and more efficient for the rest of the program to process. Then after that, we go into the region of interest determination, or error rejection. This is where we try to find the blobs on the image that might be a letter and try to figure out if these blobs are more likely just noise in the image or a letter that we should actually process. And the goal of this is to increase our accuracy as much as possible. And finally, we interpret these regions of interest. We came up with two algorithms. One of them is the contour method that we made ourselves that's really tailored to this task. Another one we experimented with is an algorithm called KNN, or K nearest neighbors. And this is one a more classic machine learning algorithm that a lot of people have used towards OCR as well. So first with pre-processing. In pre-processing, there's two main things we do. The first one is the first thing we do is we threshold the image, and this involves taking an image that's grayscale and turning it into black and white. And so this is necessary because the grayscale image not only to human eye might be clear what exactly is a U and what exactly is a letter and what exactly is the background, but to a computer that might not be as obvious. So if you turn it just to black and white, it makes it more obvious that whatever is white is probably a letter and whatever is black is probably the background. And this makes it a lot quicker to analyze. And even in the thresholding process, we kept in mind this idea of simplicity and tried to be as efficient as possible. So for example, our thresholding algorithm, we use something called Otsu thresholding, which is neither the most accurate nor the fastest algorithm, but it had a nice balance of both. It was very accurate to some extent, and also extremely fast compared to other methods, such as adaptive thresholding. Another thing we did in pre-processing is we downscaled the image. This is making a big image and turning it into a much smaller one. And this is important because you see in the leftmost image that it's very large, but even when you downscale it, it turns it into a smaller image, but you can still clearly make out what letters it is. And this is important because it makes the image much easier to work with later and also reduces the amount of noise we have from the initial image. And so continuing this idea of making everything as simple as possible, we came up in order to reject error. So we know that whatever's white might be a letter, potentially, because we thresholded it. But how can we tell if it actually is a letter? So we came up with three simple criteria to very simply reject regions of interest. So the first one is the location of letter. Because the robot is moving constantly, sometimes the letter is only half shown in the image. So a very simple criteria is this supposed quote-unquote letter at the edge of the image? If it's at the edge of the image, we know that's probably not completely shown, and the robot hasn't brought the whole thing into frame yet. So we just simply reject all of those letters. The second criteria, aspect ratio of the letter. Letters typically look more or less like a square or not that outrageous of a rectangle. If you see something that's a very long and skinny rectangle, we probably know it's not a letter. And similarly, if something looks more like a square, then there's a pretty good chance it's a letter, and we should consider it. And the third criteria is the size of the letter. We know that tiny pieces of noise, like tiny dots, probably aren't letters, and letters have a certain size that they probably are. So this criteria is also a very quick and easy method of determining whether something might be a letter. And so we see in this image, we have two images, and all of the red are these regions of interest that were immediately rejected by those three criteria that we had. And only the blue and the green were accepted past those stages. And the blue was ultimately determined not to be a letter, and only the green went through our next step, which is actually interpreting these regions of interest. So we did for that, we had two methods. I'm going to first talk about KNN, which is a more classic method of doing things like this. And so what we really do is we train the algorithm with data. So we give it a bunch of images and tells it, and we manually tell it what letter these images are. And the goal of the algorithm is to take a new image and find how similar it is to the images we already gave it. And so let's say it's similar to, and we find the three images or the K images that are most similar to it. And we say of these images, let's say the blue squares represent H's and the red triangles represent U's. Of those 5 most similar images in that outside circle, how many are H's and how many U's? Which one is it more likely to be? And that's on a high level how it works. More specifically, it takes all the images, we take all the pixel values, we convert it into data value, and we try to find the Euclidean distance between the given image and the ones we trained it on already. But that's not super important for the purpose of the talk right now. So a much simpler method compared to the algorithm we had before is this method we came up with that we call the contour analysis. So very simply, since we only have 3 letters, each of these letters have very distinctive features. If you look at H, at the top, there are 2 different contours or 2 different contiguous regions. On each side, there's 1 contiguous region. On the bottom, there's 2. And you see the signature is different for every single letter. On the S, there's 1 on both sides, and 1 on the top and bottom and 2 on both sides. And U, there's 2 on the top, 1 on each side, and 1 on the bottom. And so since there's these very specific signatures for these letters, we can not only distinguish between the letters simply by looking at each side of it, but also we can get rid of things that after a letter rejection we thought might have been letter by just simply saying, well, since it doesn't match any of these signatures, it must not be a letter. And so both of these approaches have a number of benefits and flaws, but ultimately we chose the contour method because it really most aligned with our design philosophy. Even though it was very specific to the letters we had, it worked very well with the task we were given. Not only that, it was very simple, and as some people might say, the most simple thing is the thing that's least likely to break. So that's definitely a part of the idea. And also, it easily adapts to different situations. Since it's a very broad requirement of what constitutes an H, S, or U, it very easily deals with differing fonts or transformations. Compare KNN, which, although it can be expanded to a broader character set, you could use it for all the letters of the alphabet. It's more susceptible to changes in the font size, the font type, and all that kind of stuff. So it was not as well suited for our goal of consistency. And here's a sample video of it running. As you can see, it does a good job of pulling out the letters and identifying it as the robot is moving.
All right, for the next Sorry. For the next part of this, I'm going to talk a bit about how we actually deployed all this vision software that we were just talking about onto the actual device itself. So first of all, I'm just going to briefly mention some of the challenges that normally you would have. So our main issue here is dependencies. As Daniel said, we're using the OpenCV library, and that is quite a big library that takes a decent amount of time to compile. And yeah, so as I said, these dependencies need compiling, and because this hardware that we're running it on is the ARM architecture, not the x86 that normally runs on our laptops, you can't just use the stuff that's compiled for the laptops, like the stuff that's normally found in a package manager, or like the downloads page of OpenCV. And most of the ARM builds have a bunch of different issues, like not utilizing the hardware acceleration that's available on our chip. So that using that becomes difficult, which means we need to compile it ourselves. And cross compilation, which is using a one host architecture to compile for one architecture to compile for another, say compiling for ARM from my x86 based laptop, usually it's very difficult because you need to set up all of the libraries, include paths, and all those things to get the build to work. And just generally requires a lot of fiddling, and sometimes the build just straight up doesn't work because the people who are maintaining it never even thought of you building it that way. The build scripts just straight up won't work with it. And then the last issue is that compiling these on the actual systems that they're going to be running on can be extremely slow because those systems aren't particularly powerful. Like for instance, on our first system that we were running on, we were using a Pi 0, which is which uses an older version of the ARM architecture. Compiling OpenCV took around 8 hours or so. So for when we need to keep stuff up to date, that becomes an issue. So yeah, the last problem we have here is when we have different versions of it. So again, if compiling this is a huge pain, then you're probably not going to end up compiling it very often, which usually ends up meaning that you have a different version on the target system than on the system you're developing for. Because most of our computers, we have the package installed from our package managers and keep it up to date, but our actual deployment hardware isn't up to date. So we actually ran into a problem here once when we had two different versions of OpenCV, and it wasn't even a major version bump, it was just a minor bump. And one function was behaving completely differently, which meant something that worked on our computers would not work at all and just crashed on the Pi. So we only found this out when we actually needed to update our code that was running on the Pi. So clearly this can be a bit problematic. So our solution to this was to use Docker, which is normally is used in cloud-based infrastructure, but the main point of it is that it's a containerization software that allows you to bundle all of your dependencies and your program together into this one container image. So as you can see here, the container contains all of the dependencies we need. So our actual program, the libraries, OpenCV and ROS, which are the two libraries that we use for all of our software that's running on the system. So that's all inside of this container. Essentially, it's the entire file system of a Linux system that you can move around. And you can just run this container on different hosts. So we can move it from system to system, and it should behave the exact same way, provided the kernels behave the same, which is generally a good assumption to make. So some of the advantages we have here. We can also allow these ARM containers to run on x86. So the folks at, I believe they've renamed themselves to Belina now, but they've worked on some base images for ARM that automatically will use an emulator to run the ARM images on x86. So that way, because the containers contain the entire file system, which contains the libraries and everything, we can run a fully built container for these ARM systems on x86 on our laptops. So we can test and make sure everything works correctly on our laptop and have confidence that it actually runs the same way on the real hardware, because all the execution environment is actually the same. So because we have all this emulation capability, we can also build it on x86. So again, because the container contains a full file system, the container also contains all of the stuff you need to be able to build the software. So that means we can run the build on x86, having it emulate the ARM instruction set, and build these ARM containers on commodity x86 hardware, which leads us to our last point. We can build this stuff in the cloud. So while ARM servers do exist in the cloud, they're still pretty rare and tend to be pretty expensive. Like, I think the main ARM host right now, the minimum server size you can buy is 8 cores. So clearly it's a lot easier to run stuff on x86. Like, for instance, all of the major continuous integration services like GitLab or Travis CI and whatnot for GitHub, they all have x86 build hosts by default. So that means we can run these container builds on that CI infrastructure without any additional work of, say, bringing your own CI runners for GitLab or something like that, or self-hosting and buying an enterprise license for Travis. So because of all of that stuff, we can use these containers to basically speed up our workflow. And again, because the containers contain the libraries in them, we know that when we test it by running the container on, say, our laptop, we are actually running the same version of all of our libraries that will be deployed onto the system. And we also have a couple of other random benefits, like the fact that all these deploys are atomic. So all these container images, when you deploy them, you know that they either all got pushed or none of it got pushed. So you don't have like partial upgrades, and then the same issue as we had before, where so the code was updated but the library wasn't, or the code was up there, only half the code is updated. That can't happen with a container system like what we did. All right. So now for our conclusions. So with our system going from the hardware all the way up to all the software, we strove to get basically a solution that met the task at hand and basically as little effort as possible for each system while maintaining the quality that we needed. So even though a circuit board wasn't strictly necessary, it was definitely necessary for us to get the size that we needed. And then going back to our vision system, we ditched KNN for our contours-based algorithm because it allowed us more flexibility and it was just overall simpler to maintain because we didn't have a training set. And then the Docker, while it was admittedly quite complex, it removed the complexity of having version management and library management into our system, which ultimately saved us a lot of trouble when it came to actually deploying these and making stressful changes on the spot. So yeah, I hope you learned something today from this talk. That's all we have for you. Does anyone have any questions?
The algorithms which you used, right? Is it coming with OpenCV software, or it is you build those algorithms yourself?
So Daniel, do you want to talk about this?
Yeah, can you repeat the question real quick?
The algorithms, the KNN and the other algorithm which you used, right? That does it come with OpenCV
yes,
software?
So KNN is a part of the OpenCV software. That's actually something that they implemented. But the contour method, because this is such a specific software, we use a lot of the we used a lot of the OpenCV's like built-in functions like thresholding or finding contours. But the actual analysis, it came down to actually us synthesizing the different aspects, the different functions that OpenCV gave us and turning it into actual algorithm. Anything else? All right, thank you.